And we have here Francesco Zuppichini that will talk about how to efficiently send images to GPUs. Here is Francesco.
Thank you so much. Okay, so let's do a mic check. Can you all hear me well? Nice. So today we're going to talk about how to efficiently send images to GPU. But before I forget, so these slides and my benchmark code is on GitHub. So if you think that I say something wrong, so just feel free to actually go here, open a PR, etc., and you can actually see the code I use to do all the benchmarks that we're going to see. So a couple of words about myself. I am a senior full stack machine learning engineer at Zurich Insurance. Full stack means basically that I also do a little bit of infra, web dev, etc. I work at PwC, I work at B7, I work at Plugin Face and RoboFlow as a computer vision engineers. But now there is, all language model hype, etc. So I sold my soul to insurance company, and now I'm doing also language models. That is basically just called OpenAI APIs. But at least today I can talk about computer vision again. So the plan will be that we're going to try to understand how we can actually send images as fast as possible to our GPU. So the first thing that we're going to try to understand is where are the bottlenecks in the pipeline, right? Then we're going to review how to benchmark in PyTorch, which is the best framework for machine learning. Do not use TensorFlow. Then which data type should we use for images? And finally, can we do something about memory? So, bottlenecks. I'm so sorry, I did this terrible image in Figma, and I was too lazy to make the animation, so we're going to go in Figma and move Grogu around. We are two. So we may have, So we may have three bottlenecks here. We start with images on disk. So we need to load them, right? We need to load them in memory. So, sorry, Grogu. We need to load them in memory, right? So another bottleneck may be how fast can we put and retrieve things from memory. Finally, as soon as we are ready to take our image to the GPU, we need to actually, load it from memory and send it to the GPU. If we have a lot of Grogus, right, maybe, some of this part is going to bottleneck us. So specifically for the disk, the bottleneck will be how fast can we read stuff from disk. And it's very easy to try to mitigate this, so just with money. So money always works. Very easy to buy a cheap, super fast disk. But if you read too much images at the same time, you are going to have a pool of 5 pointers that takes time. Every time you need a file, you need to basically switch to the kernel mode, make a system call, etc. You do need to keep a lot of file pointers open at the same times. For some tasks, like object detection, you have images and labels. And labels usually for object detection at least are like, in a text file, and you have just line 1, etc. So it's kind of inefficient. So later, we're going to see how we can just have like one file with all the images and man map it to memory. Memory. So memory, very important. So what we want to do, we want to reduce page fault, and we want to have contiguous virtual memory allocation, which is something that maybe, we don't remember from our system programming classes. So we're going to review very fast. So what is virtual memory and pages? So I'm terrible at explaining things. So this is just copy and paste for GPT-4. I'm going to read it. So virtual memory is an abstraction, so it is not real, right, of the computer's memory management system that allows an operating system to use both physical RAM and disk space. We don't really care about saving things to disk. To simulate a larger amount of memories, providing an applications with more memory than is physically available on the system. So you have real memory and virtual memory, and processes and programs that use virtual memory and the operating system as a mapping to know which part of virtual memory goes to the real one. Then a page is just a block in virtual memory. I think for Linux, like usually it should be 4 kilobytes. Maybe for Macs, I don't remember. And if you are going to use virtual memory in a smart way, like always placing stuff in the same way, the operating system will notice that and will try to cache pages for you and will try to, try to optimize how then you are going to use physical memory. So here, the key part is we want to try to use memory in a reliable way and in a way that the operating system can take advantage and optimize things for us. Okay, another terrible image, and so sorry about that. So in PyTorch, you usually load a bunch of images with data sets and then a data loader, right? And you don't really take advantage of putting the images in a continuous space. So every time you do an epoch, you are going to load images in a different way. So sometimes you have three Grogus there, sometimes you're 0, then maybe 4, etc., etc. So the operating system cannot really know what you want to do in the future. And if the operating system can know what you're going to do, it can make things go so much faster. If you man map, and man map means I take a file, I put this content in virtual memory, and I'm going to use it as if it was in memory. Then, if I don't find a part of that file in virtual memory, I'm just going to load it from disk, but it's always going to be in continuous virtual memory. It doesn't mean that it's going to be in continuous physical RAM, but in virtual memory, it's going to be one page after the other, right? And then just assume, I'm going to do a bunch of epochs. I'm just going to always use the same images. So it's already there, and the operating system knows how to optimize it. And we're going to see that in the end in code. Okay, super important thing. How do we benchmark stuff, right? Because we want to know how we can, send images in a fast way to the GPU, but we need some numbers. This is a hard part because people sometimes they just use the timer in Python, right? And especially when you want to benchmark stuff that goes to the GPU, you need to use the right tool. So I'm going to show you how to use the profiler in PyTorch. It's already available there. It's beautiful. In this example here, I'm just going to create a ResNet model, create some inputs, placing them on a GPU. And then we can call this context manager with profiler. We tell it, hey, we want to profile stuff on GPU and CUDA as well. Then we call this record function, and we run our model. The record function will cluster together all the operation in line 11, so right here, under the same namespace. And we can see that together, and we can see that it makes sense. So we know all the operations, that were run inside that context. Then you can print them. You can create a trace.json file, which is something very cool. It's something that you can just put in Chrome, and you can see all your trace, your program. In this case, the model. So here we have our name that we use right here. So all the operation from this line of code are under this model.inference namespace. And you can poke around and you can click on stuff, right? I want to know how much time it took to run this set of operation, etc., etc. And wonderful. It's very important to use this tool because it's also made specifically to benchmark things on GPU as well. You can also create a schedule, like to wait for a little bit, to warm up, etc., and then you pass it in the construction of the profiler. I never got it to work, so yeah, in theory you should be able to do it, but was not able to make it work. Another important thing is that we can have more namespaces. So we have one record function for inputs to CUDA. I want to know how much time it takes to send the inputs to CUDA. Make it bigger, right? Oh, okay. Sorry, I break it. And then I run it, and we can actually go again in Chrome, And we can see that this time we have two names here, so inputs to CUDA and model inference. And we can see the exact time that it took me to send my images to CUDA. And we can actually see the copy function, PyTorch, CUDA stuff, etc., etc. Okay, so for all the benchmarks, I've used this configuration. And for all of them, I run it multiple times. I do a warm-up before it. And yeah, so if you need to benchmark something in PyTorch, use the profiler. It's very cool. Now we start with the juicy stuff. So images are usually with numbers between 0 and 255, right? So unsigned int 8. But we need to convert them in floating point at some point. At least in floating point 16. So yeah, so always try to use at least the half precision version. But should we convert them before we send to the GPU? We send them to the GPU, or we don't convert them, we send to the GPU and then we convert them to floating point numbers. So creating some images. First line of code. Then this is an optimized version of doing that. So I have images in assigned int 8. Do I convert it to half precision on GPU and then I send them to GPU? Or do I just send them to GPU and then I convert to CPU? What do you think? Should we convert them first to floating point and send them to GPU? Or vice? Yeah, if you want to raise your hand for the first one, no, you're okay. Or should we just send the unsigned 8 images to GPU and then we convert them on GPU? Okay. Little bit of confusion there. Yeah. I actually asked on LinkedIn. Yeah, it was 50-50. So a lot of confusion. So I just tried. And let's zoom it here. So green line is I convert my images on GPU. So I have my unsigned int 8 image, numbers between 0 and 255, send them to the GPU, and then I convert them to floating point. Which makes sense, it's so much faster, right? It's 2x, because you're sending less data. An unsigned int 8 will be it will be smaller than a floating point number image. So yeah, you should do this, but in practice, another interesting thing about when you benchmark stuff is that here, it seems that, I get here, 4 times speed boost by just doing this instead of this. It's just changing 2 words, basically. But if you benchmark it, when you are training, the reality is different. So here I'm just creating a data set in PyTorch. This is not really important. It's just the way that you in PyTorch create just load images in PyTorch. Then I have a training function here, training mix precisions, etc., etc. Not really important. The important part is the benchmark. And sorry again, my plots are not so nice, but yeah. So what I did is I'm training 2 models. I'm training a ResNet 18, a ResNet 50. So still not super big models, but it just takes so long to run this, so I didn't have more time. And I have a bunch of batch sizes between 8 to 64, and a lot of image sizes as well. So I want to know, given different type of models, batch sizes, and images, which one is really faster when you train? Because when you train a model on GPU, the model is training, but in the meantime, you actually send data. So there is some kind of So while you train, so you are also putting data there. So in theory, the smaller the model, the less time you have to send data. So in theory, the smallest the model and the bigger the images, the bottleneck is in sending data. Any kind of makes sense. So let's have a look at the plots here. So this plot is for images with size 384, which is not really big, especially in 2024. And we can see, so these 2 guys are ResNet 18. The green one is the one in which we convert the image on GPU, and we send on GPU unsigned int8. And it's faster. It's around a 10% gain. It's a no-brainer. And same thing for REST-50, same thing. And the more we increase the image size, so we went from 384 on the left benchmark, and 640 and 480 on the second benchmark. The more data we want to send to the GPU, the faster will be to just send it as unsigned int8. And with a very big image, like an HD one, the gap is just way bigger. And there, my computer just crashed because the batch size was too big. Yeah, so if you can, do not convert to floating point. Number your images before you send them to the GPU, and just send as unsigned int8. But we need to do data augmentations. So most of them, like a random crop, a resize, rotation, blower, whatever, they just move pixels, so they not change the data type. And you can run them on GPU if you want, or you can run them on CPU. No normalization has to have a floating point number as an input. If you want to normalize on CPU, you can send an image as unsigned int8, right? Because then you cannot just do the normalization and then reconvert to assigned int8. You will just lose some information. So in my opinion, yeah. So this, I don't know if people know about the transformation in PyTorch, but since I guess one year or even more, if you pass a tensor, so they're just gonna run some PyTorch code, so you can do transformation in batches, CPU and GPU, and you can also go ahead and export that to Onyx because they're just PyTorch code. So what we can do is to normalize in front of the model on GPU in this way, right? So here I'm just taking my REST-18 small, putting a normalization layer in front of it, and then I'm gonna put it to the GPU, and here I'm just sending some input as well. This has another good advantage for production. A lot of time when you want to put a model into production, you export it to Onyx, then you have some sort of server or whatever, but your images, they need to be pre-processed, right? So it's always a pain in the to install NumPy or Pillar or whatever, and to have just have more dependencies in your production server. Here you can just put your PyTorch, your transformation in front of your model, and you export it to Onyx, and you don't need to do additional pre-processing on your server. Okay. So to recap, always better to just send the image as assigned int8 again, and run the normalization part on the model. Now, another question would be, what about image quality? So let's retake Grogu. And what I did, I went from my original very big Grogu full HD picture, non-compress, and do a compression step using the FFmpeg library. I went from 3.5 megabytes on the left to 107 kilobytes on the right, and they look identical. If I zoom it, it's always cute Grogu. So in theory, we will think I'm compressing images. They are going to be faster to load because they are more lightweight. And I thought that as well. So let's get a dataset, and let's do a benchmark. Again, just checking the throughput of my dataset in a data loader in PyTorch. Now, these two guys are for images of size 640, 480, and the guy on the top is the uncompressed one, and the guy on the bottom is loading images that we compress. For some reason, this configuration here is just super fast. I think I run it 3 times, So I have no idea why this set of parameters just make my throughput so high. But this is counterintuitive because uncompressed images that are so much bigger, they are loading around, it's faster, right? It's always here on the bottom. And here is the same thing. These are these are uncompressed full HD images, and these are full HD compressed images. So I thought, why? So why is that? When we load a JPEG compressed image, we need to pay the price to do the parsing of JPEG, because JPEG is a compression file format, and we need to pre-process it. If you load an uncompressed image, you just load it and you convert to a PyTorch tensor, and that's it. So again, since that we don't need to compress images if we don't care about saving space of disk. Memory. What about memory? Yeah, what about it? So we want to try to optimize memory. And so what we are going to do, we're going to take a folder of images, the same images that we load, so like a folder with 1K Grogus, and we want to create just a file with all the images and map it to memory. In order to do this, I'm going to use a very nice package made by Vincent Moens, which is he's an engineer at Facebook, Meta, whatever it's called now, and it's called TensorDict. And what you can do with TensorDict is just a TensorDict. So it's like a tensor, but made of a dictionary. You can just, you can just create a tensor with some key values, just passing a dictionary inside, and you can use it as if it was a real tensor, which is very convenient. But for us, it's more convenient because you actually implement a way, to given a TensorDict, so just a tensor with a dictionary inside, to map it to disk, so I don't have to write it. More low-level way to do this will be I will just do that in NumPy, which has support for mapping vectors to disk. But here I've just taken advantage of this package. It's already provided to me. And I can map stuff to disk, and then I can load it. And this is what it looks like. We have our two tensors, so Q1 and Q2, right there, stored to disk. Just in a way that I can just load it, and then it will be in continuous virtual memory, and some metadata about them. Okay, so let's see some code to take our data set of images and map it to disk. Sorry, map it to memory and save it to disk. We are taking advantage of basically this code from Vincent framework, in which we say, hey, I would like to have a tensor, an empty one, that is of the size of the data set. So in my case will be 1,000 images, because I have 1,000 images of Grogu on disk. And then just whatever the shape of the images is going to be. Same thing for the targets. For me, it's just a tensor with one. And then I create a data loader. I use my data set from PyTorch to load all my images, and then I will just take batch after batch of images and put it in my map tensor. So I'm going to have a map tensor with all the 1,000 images one after the other. Why I want to do that? Because I can just load one single file. I will just have one file for images, and where it is, one file for images. No, sorry, it's not here. It's on my other computer. I'm going to have one big file with all the images and one big file with all the labels. So I just need to load two files, and not 1,000 files for 1,000 images, 1,000 files for 1,000 labels, or whatever. And they're going to be continuous virtual memory. So every iteration I do, I will always refer to the same part. The operating system will know which part I will going to use, and will make things so much faster for me. Now, in order to use this this tensor that we created, that is going to be a dictionary with images and targets, we need to write some little additional complexity. This is just some boring stuff. So for some reason, we need to, if we want to use more processes in the data loader that is going to load our memmap tensor, we need to set the start methods to spam. I don't know why. It's just the way it is. To use it, we create our PyTorch normal dataset. We create our TensorDict data type that is memmap to disk. We create a data loader, and we also have to set persist workers to true for some reason. And then we can just iterate the data loader, and we are going to use our memmap tensor, and that's it. Yeah. So benchmarking it, how much faster it is? How much faster is to load memmap files compared to the normal way everybody is doing it? Sorry, again, my plotting code is terrible. It was made by GPT-4. Yeah, so if you are a data scientist, I think that you should not be afraid of GPT-4 taking over your job yet. Again, so these two guys on the bottom, better, the guy on the bottom is bandwidth of loading images without memmapping them. So just the normal PyTorch way of doing things. This is for small images, this for big images. Sorry, these two guys there, the biggest one. The guys on the bottom are the okay, I'm sorry. So them, I'm really terrible at making plots. I should read the caption. Okay, these two lines are bed size of loading small images, 640 times 480. Bottom one is loading from a memmap file. The top one is just the normal way of loading all the images. This is a 2.5x improvement, more or less. Bigger the images, bigger the gap, of course. So this is the plot of loading memmap full HD images and not memmap normal, always full HD data, but with the normal PyTorch way. And here I have the same plot, but here I also send the images to the GPU. I'm also sending the images to the GPU as well in order to check if something changed between just loading them on CPU or also see, when I send them to GPU. Nice thing is that it's always really so much faster. So this is the memmap one for small images, non-memmap one for small images. It's 2x improvement. Same thing as well. It's really, really so much faster. It's really incredible. Oh boy. So, to wrap it up, how to send images efficiently to the GPU? Try to send them as unsigned int8. Try to do the normalization step on the model or whatever step is going to require an image of a floating point number. Don't compress images, which is still something a little bit weird to me. And try to memmap all your images to the same file. And that is going to be probably the biggest performance gain that you can actually get. And it's great that not really a lot of people know about this. And so that's it. Thank you.
Thank you, Francesco. Okay. Okay. Thank you, Francesco. Any questions? We'll wait for the mic. I have a mic for the questions so that people at home can listen.
Hi, thank you for your talk. It was very interesting. So I have a question. I come from the video game industry, so I've always used the GPUs for, I would say, for what they're meant, for rendering zombies and making their heads explode. But, but anyways, I have had the problem, of course, of sending textures to the GPUs and rendering the images from there. And I'm wondering whether you also tried something in between JPEG and uncompressed, which is some format like DXT, which is meant to be compressed somehow, but stay the same inside the GPU. And the GPU can sample the image without altering the data. And it's a quite efficient way. There are many also variants of it, but I'm just wondering whether you have considered also that.
No, because I didn't know that that was a thing. I never heard of it. And this is actually, so I think that there is a gap between people doing machine learning, etc., and people doing like real optimization stuff. One thing I was thinking about is that I can just send the JPEG bytes to the GPU and do the loading there. So but I still have to try that.
Yeah, I mean the format is called DXT. There is the DXT1 for black and white, DXT4 for color and alpha images, but there are also other variants and also other more recent formats. I mean, they have the actual requirements to be the same from when you load it to when you upload them to the GPU. So it might be worth a try. Okay.
Thank you. Yeah.
Thank you.
Okay, so video game industry and machine learning should talk a little bit. Okay, any other questions for Francesco? Okay, Merve.
Thanks a lot for this talk. I wanted to ask, this might be irrelevant to the topic, but like a meta question. So you said you use Torch Profiler, right? Whenever I do benchmarks, I use Torch CUDA event, and then it's like a mark, like setting a mark between events, and then you synchronize. Is there a reason why you specifically used Profiler, or like I feel like it adds an additional complexity rather than directly using CUDA synchronize? So I want to ask that. Thank you.
Yeah, so you can also use the benchmark timer, I think. The reason I use the profiler is that you usually want to use the profiler so when you want to look at all the operations and try to optimize the runtime, because you can actually see all the operation right. So this is why I use it. So I was also looking at the tracing here to just get an idea on when things happen at the same time. And yeah.
Thank you.
Okay, any other question for Francesco from the audience? Yeah, Luca. Thank you.
Ciao Fra, I wanted you to delve a bit deeper in the TensorDict lib. Is it a bit like Hugging Face datasets, or I mean, it's a bit more than that, but if you could just talk a bit about it a bit more and then compare with what's already existing. Thank you.
Yeah, so thank you so much for the question. Oh my God. Okay, so the history of this framework is that Vincent is working on the reinforcement learning PyTorch framework, and they had to develop an efficient way to send tensor across computer nodes, etc., etc. And so they just code this TensorDict because they need to send more tensor at the same time. And they also needed to do normal tensor operation like reshaping, etc., etc., without having to go through each tensor and do that individually. The documentation is pretty good. Oh boy. Yeah, ovviamente. And they developed the main mapping feature to get one single file that they can share across these nodes doing whatever reinforcement learning things they have to do. And that is very efficient because you just need to send just one file per tensor, and you redo the mapping on the new process. It's not like Hugging Face dataset. So Hugging Face dataset is a library for datasets, to have, I think they use pi-arrow format, etc., etc. So it's optimized to share data and load them. In this case, you already have tensors. And you just want to, to have a better way to cluster them together.
And so when you exchange the memory map file across nodes, right, do you also need to, basically, it
In my
contains
case,
metadata
I'm
about
not
the
doing
location?
I just have a GPU.
Oh, yes, okay.
my computer,
It was more
right?
of a theoretical question,
Yeah.
but okay.
Theoretically, yeah, they have some example in the documentation with some code, with weird-looking code that just send tensor around, and yeah, that you can look into if you want to. It was very intimidating, so.
Yeah, definitely. I can reckon. Thank you.
Okay. Any other question? Any other curiosity from Francesco? Okay, I think that we are right on time, so we can close this session. Thank you, Francesco, and a big applause.